Okay, I guess we can get started. Okay, so today is the last lecture on transforms. So finally going over a big hurdle, and then after the midterm we'll start with control theory, and I think we'll have time to do a big chunk of probability and then information theory. So it'll work out fine. So I'm going to continue with the aliasing, and actually not aliasing as much as the equivalent to this Nyquist rate. How fast should you sample? So we'll talk about that. Then talk about the discrete Fourier transform, and then a specific way of doing the discrete Fourier transform called the fast Fourier transform, and finally the Z transform or the Z transform, depending on which country you're from. I think I'll use both interchangeably because I can't keep it straight in my head. I studied it as a Z transform, and then over here I studied it as a Z transform, and I can't keep it straight anymore. So I'll just keep flipping around. Okay, so I'm going to start with the notion of Nyquist rate. I want to actually give you a visual depiction which will hopefully clarify things, and let me explain what's going on. So what we have over here is some continuous function of time. So we started out studying this from the perspective of a discrete function of time, but I'm going to actually give you a different perspective. So I have some continuous function of time, let's say this over here, and what I want to do is to send it across a channel that only communicates digital information, so digital bits. For example, this could be a symphony orchestra, playing something, and you want to make a CD out of it. Or if you want some other kind of music, it doesn't matter. Some kind of music, and you want to put it on a CD. And so what I'm going to have to do is to essentially sample it. So one thing I told you was what Bell discovered, the kind of a big deal, was that we don't really need to do a harmonic analysis as they were doing. We don't need to figure out all the different instruments that are playing. All we need to do is to essentially just figure out the different levels at which you're playing and send this. And and what Bell did was to do it continuously, but what we want to do is to do it discretely. So what we're going to do is we're going to sample it as frequently, okay? And I'm just drawing this over here, and this is going to give us something like this. So it's going to give us these discrete samples, and I'm not going to show all the samples. Something like that, like a mess of dots over there, right? But the discrete samples. So one obvious question one could have, this is now, let me just draw this is x of t, and that's t, and this is going to be x of square bracket nt, where t is the sample period, and this is time, of course, continuous time. So one question one could ask would be, let's say you make a particular sampling rate, you choose 44 kilohertz sampling rate for your music, and you make a CD of it, and somebody says, oh, that music is no good, it's not sampled fast enough. You can't really hear everything that's in the music, something is missing. In other words, what should be the sampling rate such that the entire signal xt is preserved in its completeness, and what you're going to do when we recreate it at the other end is identical, right? That's the question you want to ask. So we have this question. Is the sampling rate fast enough? For instance, you could sort of visually see if the sampling rate were like this, this space like so, it's certainly missing all the stuff in between. So what are we missing exactly, right? So what is too slow, what is too fast? It's a non-trivial problem. The beauty of what we're going to study is that the transform domain gives us a solution which is mathematically correct, and it's very nice. What we're saying over here is that let us suppose that the transform for this is going to be something like this, okay? And I'm going to actually draw it like this. I'm going to show the positive, negative omega, and I'll tell you why positive, negative in just a moment, so just bear with me. Let's say that has some particular shape, and let's say that this is the omega L is the support. This is sort of where in the frequency domain it is. What we say is that this is obtained, this particular is obtained by actually x nt equals xt st t, where xt is being multiplied by the sample train, s sub t, the impulse train, which is separated in time by capital T over here. So this is what we're saying. We're saying this over here is basically this is product. And so we're saying that in the frequency domain, this is a convolution. And it's a convolution of the impulse train, and that leads to the following situation. It leads to this particular shape, okay, being replicated over and over again, and the spacing between these is going to be omega s, where the smaller capital T is, the larger omega s is. It's further apart, right? If you make it smaller and smaller capital T, because omega s is just 2 pi over capital T. So the smaller capital T is, the further apart the space, right? And so we can now say that this sampling, so this corresponds to this, and this corresponds to this, and now we can ask the question, we can answer the question of what is fast enough. What we're saying is fast enough is this. If over here what I do is that I can take any one sample like so, just this section over here in this band, I ignored everything else over here, and from this I do the inverse transform. When I do the inverse transform of this, I'm going to get back x of t, whatever that looks like. Why? Because I went from here to here, right? And the inverse transform, when I go from here to here, is going to give me back the transform, because transform and its inverse are exactly mathematically equivalent, right? So whatever I have here, I'm going to get over here, right? So what I'm saying is that if I sample it such that these transform domain representations are non-overlapping, then I can just take any one copy. And how do I do that? I do this using a band pass filter. Band pass filter says, give me this set of frequencies, nothing before it, nothing after it. Ideally, it exactly takes that band, but of course, in reality, it won't be exactly that much. But nevertheless, I can take this part and get it over here. That's a really neat trick. What I've done is I've sampled it, right? I've sampled it, so I don't have the continuous quantity anymore. I only have the discrete quantities. Yet, by doing a band pass filter, I can recover the original signal exactly as it was. So when somebody comes to you and they say, hey, listen, you know, you sampled this particular piece of music and you gave me these samples, how do I know? How do I know it's good enough? What you would say is, okay, let's look at the original piece of music, x of t, and let's compute its transform and look at the support, what frequency band it occupies. If my sampling rate, omega s, is greater than twice this omega L, right, then I can claim to you that what I'm going to play back from my speakers is identical to the original in every respect. It's mathematically identical function, okay? And that's what is called the Nyquist rate. What Nyquist proved was that as long as omega s is greater than or equal to 2 omega L, we are basically in very good shape, okay? And this is the basis for, you know, MPEGs and JPEGs and everything, right? Because essentially, though I won't talk about it today, a picture, an analog picture that you take with a camera on your silver iodide film, you know, which is your old analog film camera, and a digital camera, as long as the sampling rate, where the signal over here corresponds to basically the picture elements in that picture, is fast enough, you know, you have a high enough megapixel camera, you will in fact get exactly what's in the digital picture, analog picture. There's no difference between the two, as long as you have this condition over here. And this is the Nyquist condition, omega s greater than 2 omega L. Okay, so one question that immediately arises is, okay, why this 2? Where did that 2 come from? And the second question is this, what happens in practice? You know, do we really meet this criteria or not? So to understand the 2, I'm not going to give you a very precise mathematical definition, but I'm going to give you an intuition of what's going on. And to understand that, let's take a look at the Laplace transform, or the Fourier transform corresponding to a sinusoid. So if you have a sinusoid like this, okay, this is well, this is, I guess, minus sine x or something like that, or minus cos x. It doesn't matter. The corresponding transform is actually going to be having 2. So if this has a fundamental frequency of a fundamental period of t, then this is going to be 2 pi delta plus minus omega naught, where omega naught equals 2 pi over t. So a sinusoid in the time domain corresponds to 2 deltas in the transform domain, okay, which are going to be separated by this omega naught over here. So this is going to be minus omega naught, it's going to be plus omega naught, okay. And so the gap actually is 2 omega naught. It's not omega naught, it's 2 omega naught is the gap between these two deltas. Now if we have a complicated function like this, then we can imagine, let's say it's a periodic complicated function for the sake of argument. It's going to look like a bunch of, the Fourier series is going to have a bunch of sinusoidals underlying it. And if it's a aperiodic one, then you have Fourier transform, which we can think of as the integral of an infinite number of sinusoids underlying it. But each kind of basic sinusoid corresponds to what? A delta function, right? Which is separated plus minus omega. So if we can think of the energy of this aperiodic function being focused in some regime, it's going to be actually twice. It's going to have some positive component and some negative component. And typically it will be symmetric along the 0. In fact, it will be symmetric along this j-axis over here. And so that's why you get this 2 over here, okay? And that's why you typically have this kind of symmetric function around the 0, because the sinusoidal, which is the basic building block of the transform, has got this symmetricity over here. Now you might say, how do we get negative frequency? What happens is we actually are going to frequency shift the whole thing over. Okay, we're going to frequency shift it by adding it to some kind of carrier. It's not important how that's done, but the electronic circuits that do it. But this gap of 2 is preserved. Okay, and so intuitively what's going on is that we have some signal. We compute the transform. The transform is going to have essentially some support, which is half in the negative frequency range, half in the positive frequency range, because of the fact that the basic sinusoidal has got that same kind of dispersion, one in the positive, one in the negative. The 2 pi delta, this delta over here, plus minus omega naught, is going to create that. And consequently, when we do the frequency shift like this, we can do frequency shift by sampling and then doing band passing. Okay, that's going to give you frequency shift as well, because this infinity replicates the frequency over and over again. So I can just pick any frequency I want and just grab it from there. Certainly that's one way of doing it. The other ways of doing it using what I call mixer circuits. But at any rate, once we have this, we need to get this 2 over here into the Nyquist rate. So the what is omega L? Omega L can be thought of as being sort of this. So actually, this is going to be 2 omega. Omega L is the support of the. Let me make sure I get this right. Yeah. So this plus minus omega L. So omega L would be the fastest. I'm sorry. Frequency inherent in the signal. Okay. Now. Okay, so let me stop here. Are there any questions about this so far here? So hopefully the intuition is becoming somewhat clear. The other question is, what happens in practice? Do we actually have frequency limited signals in practice? And the answer is no. Okay, and the answer is no, because even if you think about a simple pulse, if you take a simple pulse as the actual signal over here, like this, then the pulse, of course, this is going to negative 0. It's acausal, but we can always time shift it. This corresponds to the sinc function, and the sinc function is infinite, right? So we actually are not going to be frequency limited. So but we can sort of take some section of it and say everything beyond it is too small to worry about. Okay, and so in practice, what we need to do is to find a sampling frequency fast enough so that there's not too much energy. Okay, there's not too much energy in the sampling period. So if you say, okay, this is going to be omega L, this is going to be 2 omega L, okay, like so, then everything else I'm ignoring, that will cause some distortion. Okay, and so when you're doing this sampling, so when you have a CD, if you try to digitize any analog input, you'll find that they'll say, what rate do you want? Do you want 44 kilohertz? You want 136 kilohertz? Whatever. You can choose a different frequency, sampling frequencies. And the faster you sample, basically you're making this wider, you're making this omega S bigger and bigger. Okay, and so you're basically getting capturing more and more of the underlying harmonics of the signal. And so you pick it big enough so that you're not going to lose anything. Now the human auditory system has a bandwidth of about 40 kilohertz. Okay, basically you can't hear, 20 kilohertz. You can't really hear anything beyond 20 kilohertz, 20 kilocycles per second. You can't really hear it for most people. So if you sample twice that, okay, so 22 is the range for most people, 44 kilohertz is what you get, and that's the typical CD sampling rate is in fact 44 kilohertz, because what we're saying is that anything that goes above 22 kilohertz, any energy beyond that range, you can't really hear it at all. It's just too high pitched for you to hear it, so you don't really care. And what people argue is that a pure analog medium like a LP, like a vinyl disc, has got this actual analog signal on it. So all frequencies are preserved, even up to 100 kilohertz or 1 megahertz. So if you're a purist, you'll say, oh, I want the entire actual analog signal, because that is exactly what was happening, because the way the LP is working is there is actually a groove, and the height of the groove is proportional to the sound pressure, and that is the real. Whereas this is an integer, right? So obviously this has more, but then what Nyquist would say is, if you can't hear it, why do you want to preserve it? And so we don't have a sampling. Now you can sample at 130 kilohertz or whatever if you wish to, but presumably you can't really hear it. Okay. Same thing is true for JPEGs, where what we do is that all the high frequency visual components, in other words, the variations that are too small to see are hidden. You don't actually see them. Okay. And when you hide it, you're getting rid of some of the visual frequency, again because our eyes have a particular cutoff. They can't see beyond a particular visual frequency range, okay, which corresponds in this case to the spacing rather than the sound. And same thing for movies. If you have a digital TV, once in a while you'll see these big blobs. You'll see these big blobs. How many of you have seen it? If there's motion, you've seen this square or rectangles, right? Everybody's seen those? Okay, what's going on is that those are the first few Fourier coefficients that are being sent, because what's being sent is the first few Fourier coefficients. So in the sampling, what we're going to do is in the frequency domain, well, I'm not going to. So what we do is we send most of the information is in this first coefficient, and the next coefficient, etc. And the higher the frequency you send, the more detail is filled in. Okay, this is what's called progressive scanning, a progressive transmission. And if you have packet loss, what happens is you've lost the higher frequency components. And so what you see is the low frequency blocks. And so you see those blocks over there. Okay, so and that's because of the transform that's being used as a discrete cosine transform. And you lost the high frequency stuff. Okay, yeah.
So if we send the transform in digital form, we still lose the exact values between the, inside, between the samples.
No, that's the thing. If you sample fast enough, there is nothing, and you're not losing anything. And the way to...
How are you sending the transform?
In between.
Form?
Right. So what we do is this... let me expand on this a little bit to explain what's going on. Okay, so I'll just use the same figure actually, and it'll become clear. Let's say the signal was just a sinusoid, okay? It was just a simple sinusoid, something like this, okay? All we need to send is exactly one bit of information, one piece of information, which is what's the frequency, right? Or the period. It doesn't really matter, right? So you agree that if I send you just that one piece of information, I can completely recreate the sinusoid, right? Even though I'm only sampling it at this, very infrequently. In fact, I need to sample it, right, at only that, or 2 omega. So omega is over here. So this is the time period from here to here, right? This is the time period t. I just need to sample it twice. I need to sample at the peak and the trough twice. That's all. Yet I can completely recreate it, because I'm telling you, it's only sinusoid. There are no higher frequency components, right?
But in this case, the transform is very simple like this.
Yes, it is. Let me finish. Okay, so you got that, right? That I'll call the base frequency, okay? Now what I'm going to do is I'm going to make it more complicated. I'm going to add a second component where we have a higher frequency thing, okay? Where we have, let's say, something like this. This is at twice the frequency, okay? And it's at a particular amplitude. So the sum of these two is going to look kind of more complicated, right? Because it's going to go up like this, and then it's going down here, so it won't be like this. It'll go down, and then something like that. Okay, you can see that if we were to use yellow to show the sum, it's going to look something like that. It's going to give, okay? You see this yellow shape? That looks more complicated, but actually it only has two components. It has the primary and the harmonic. I need to send just two numbers. The amplitude corresponding to the first, and then the amplitude corresponding to the second, because those are two deltas like that, right? This is at plus minus minus plus minus, this is minus 2 omega naught, and this is plus 2 omega naught. Okay? Now, this is for a periodic signal. If I make it aperiodic, these deltas are going to become into a shape. They're going to fuse together, and we're going to get some kind of thing like that. Okay, but the span is still going to be 2 omega naught. Okay, if it's aperiodic. Because what happens is, remember, the shape is preserved, but we're going to move the deltas closer together. It's like if you remember from the rectangular pulse, when you have single pulse, we have a shape of a sinc function. As we make the period larger and larger, the deltas come closer and closer together, but the shape is the same, right? So the envelope, whatever the envelope is, this is the envelope over here. This envelope is going to be preserved independent of the periodicity. Okay?
So what I'm not clear about is how you send this complex envelope.
Okay, so what I'm going to do, what I am doing here is I'm not sending the complex number exactly. What I'm doing is that I'm going to be sending the time domain values like this, which are the samples. Okay, we're not sending those numbers over here. So this yellow stuff is all the math. Okay. What happens in practice is I'm going to actually only send these sample values. What's on the CD is not the transform. What's in the CD is these time samples, right? However, this allows us to understand how fast we need to send it. Okay, and so the it's this funny thing. So when I have the sinusoidal, I'm actually sending the sine wave. I'm only sending essentially the peaks and troughs. Okay, because that's all I need to sample, and yet it's going to be enough. But what I will hear will be the sine wave. Okay, that's sort of magic, but that's the Nyquist. We are not sending the transform. We're actually sampling it. We're telling you how fast to sample. Okay. I know it doesn't seem to make sense either. That for a sine you just send the positive, negative, and that's all you're sending, and yet that's what the Nyquist rate says. We just need to send that much. Okay. Any other questions about this? So this shows up all over the place once you do signal processing and so on, and we won't go there. The only kind of the main takeaway from this, from the perspective of a system and so on, is that if you have a continuous signal, and most signals are continuous, try and figure out what the frequency range it spans. What is the support in the transform domain, which would be omega L, and you should choose the sampling frequency at least twice as much, and that's the Nyquist criterion for it. Okay. I'm going to now continue with the discrete Fourier transform. Right. So let me just remind you of what we were doing, just to sort of set the stage. We started out with this notion of a periodic signal, and that's some signal over time, which is repeated, and this corresponds to the Fourier series. We can think of it as being a sum of discrete sinusoids. So it's sum of, maybe I should write it like this. It's a sigma of sinusoids. And then when you have an aperiodic, which happens only once, you get the Fourier transform. And so this is the integral of sinusoids or complex exponentials, which amount to the same thing. So now we're going to, and then we looked at this notion of a discrete. Okay, here we are, and this is a discrete function of time, x and t. This is xt. When we have a discrete function of time, what we have is the discrete time Fourier transform. And this is again going to be sigma of, let's me call it complex exponentials. Okay. Now we have one more case where so by the way, this function could be basically any function, right? We're not really saying exactly what it is. But what we have is, let's say that we have a discrete function, and moreover, it's either time limited or it's a periodic, and thirdly, if it's time limited, let's say the duration is some t, and the periodic, then the period is t. Okay, and moreover, we want to do the transform. Sorry, time period. We want the duration. So what I'm going to do, t or t naught. Let me see. So t naught. Sorry, t naught, and t naught is a multiple of the sampling period. Which means t naught, we'll just call it capital N, t, where as before, t is the sampling period over here. This is t, this is 2t, etc. So that's a discrete time Fourier. So it's discrete like here, and so we can look up this, we can think of the signal as being something like this, for example. And that's it. That's all the signal there is. Okay. So in this case, this is t, 2t, 3t, 4t, 5t, 6t, 7t, and I guess this is 0t, whatever. So there are 8 values. So t naught equals 8. Sorry, in this case, 8t. So 70, what am I doing here? So I have 8 values. So how did I get, I'm missing something here. I always hate when this happens. Okay, so there are 8 values, but the span is 7t. So the 70, and we have 8 values because we have one at the beginning and one at the end. So the time period is 7 times, but you have 8 values. Okay, we have, so I think I should start from 1 and then I'll get it to work out properly. N minus 1t. Right, so we'll call this x of n minus 1t. So actually I guess t naught should be not nt but n minus 1t. I hate this off by 1 mistake. Yes?
I think it's 80 because I have to count the t after plus 70.
Let me just try and remember, because you can do it either way, right? So I want to specify the sample at n instance, which are x0 to xn minus 1. So that's what I'm defining it to be the same. We didn't define the period to be nt. So this is x0t and xn minus 1t. And then I guess we have over here, I'll define the t ought not equals nt. So I'm going to just get away from this whole off by 1 by definitions. Okay, we'll just say it's nt, makes life easier for us. And certainly that's the way, that's what the standard thing. So, okay, so what we're saying is that the signal has got values only at 8 time periods, or 8 times 0 to 7, and we'll define basically t naught to be nt, where n in this case is 8, because 8 is the number of instances defined. It's time limited, it doesn't happen, afterwards it's gone. Or if it's not gone, then it repeats itself over and over again, okay, with this same, form. And we have, this is a multiple of the sampling period, okay, multiple of sampling period, so it's a multiple, it's in this case 8, and we define n to be basically such that the last value is n minus 1 times capital T. Okay. All right. So if all this is true, then it turns out that in the frequency domain, this particular thing corresponds to a set of frequencies, omega, in the omega plane, which are discrete as well. And there's only, inside there's actually the same number of them as well. Okay, so we have, in this case, a set of discrete frequencies corresponding to it. So here, we didn't really say what the frequencies were. Okay, we were not precise about what frequencies are being used. In the discrete time and frequency Fourier transform, we say that the function has got a discrete set of frequencies, and that actually simplifies everything quite a bit, because we now know that all the frequencies over here are going to be some multiple of the base value omega naught. So it's omega naught, 2 omega naught, 3 omega naught, etc. And that's going to be the set of discrete frequencies that correspond to this. Correspond to this function over here. And this is what we call the discrete. And I'll put D in quotes. When you say discrete, in this case, you're saying discrete in time and discrete in frequency. Okay, and so it's called a discrete Fourier transform, a DFT. And let me give the actual definition now. So is this clear over here? So we're going from sort of continuous, periodic, continuous aperiodic, discrete, but we don't specify that it's periodic or not. And this is either discrete time limit or discrete periodic, and this multiple, and then we get the discrete transform. And in most cases, what we can do is we can arrange for this to be true. Okay, so this particular discrete Fourier transform, discrete time Fourier transform, is not very commonly used. Okay, the only reason to study it, from my perspective, is that because it's useful to study the DFT. Okay, and DFT is what's used in practice. So everything I told you about, JPEGs and FX, everything are actually discrete Fourier transforms. In fact, a specific variety of those called discrete cosine transforms is what we use, but it's a kind of a variant of the discrete Fourier transform, because you can always arrange because all real functions are time limited anyway, and we can always arrange for the sampling period to be some submultiple of t0, and we can sort of ignore anything else at the end. If the sampling period is fast enough, so a little bit left over, we just ignore it. So this is always going to be true. So this case actually rarely arises in practice. Okay, having said that, we can now write down the discrete Fourier transform. And unfortunately, the notation for this is quite messy, but here is what it is. So we say x, j, k, omega naught, and explain what that is in just a minute. This is 1 over nt, and we're going to have a discrete sum, and the sum is not infinite. It's actually has n terms in it, and it's going to be x nt. So that's, as usual, we have the x value multiplied by a complex exponential as usual, and in this case it will be e to the minus jk omega naught nt. Okay, so this looks kind of messy, and let me try and explain what's going on if you kind of parse it. So this is just notation. We're saying x is a function of jk omega naught. So j means that we're going to use a complex exponential, and k omega naught is showing that it's a bunch of discrete frequencies. Why? Because as I showed over here, we have omega naught, 2 omega naught, so on until k omega naught. So that's indicating that it is it's a function, and this k is sort of the kth value of the transform. Okay, they're going to be multiple values. This is the kth value of the transform, and we have a sort of a summation n is equal to 0 to n minus 1 x n t, and then we are saying, okay, we're going to take so what's varying over here is this n. The k is not varying, the kth is fixed, and so it's a complex exponential where we have a bunch of frequencies, and the frequencies are going to be corresponding to the n equals 0 to n minus 1, which actually is corresponding to the nth value of x. So x nt is the nth small nth value of x, and that's multiplied by e to the power